thank you so much, everyone, for taking the time out of your schedules to attend this session, another session of Community and Climate. My name is Jack. I'm a librarian here with the Sunnyvale Public Library. I'm very pleased to welcome you to this program to discuss all things batteries and clean energy. To present this evening, we have a very special guest. He's a professor of environmental studies at Wellesley College, as well as a historian working on topics such as climate change, the clean energy transition, and environmental politics. He is also the author of Charged, A History of Batteries and Lessons for a Clean Future. Dr. Jay Turner is here with us tonight. Howdy, Jay. Thank you so much for being here. Before I have him properly introduce himself, sorry, Jay, I do have a little bit more about to share about his work. His current research focuses on prospects for and challenges ahead for a clean energy future, and his public-facing work has appeared in many publications and venues, including Science, the New York Times, Natural History, Lapham's Quarterly, Literary Hub, and The Conversation. In addition to all of this, he is the president of the American Society for Environmental History. So, once again, before we start in earnest, we do ask that you turn off your cameras and mute yourself during the presentation. If you do have any questions, please feel free to place them into the chat, and we will make sure to attend to those towards the end of the talk. With that, Dr. Turner, I will let you take it from here whenever you are ready.
Thanks, Jack. Well, and thanks to everybody for being here. Yeah, I really appreciate the invitation. I was hearing from Jack just a little bit about the series that I'm speaking as a part of, and it sounds like a great series, a wide-ranging series, touching on just a whole bunch of different topics important to sustainability. So glad to have a chance to talk about batteries this evening. Yeah, so as Jack said, actually, maybe I'll go ahead and share my screen. I've got some slides that I'm going to share with you all. There they are. I thought I would start off and just give you the high points of this book that I had a lot of fun. I learned a lot writing, really helped me think about batteries and materials and both, the possibilities for and the challenges of the energy transition ahead. So I thought I'd spend, roughly half an hour kind of going through these slides, kind of hitting some of the high points, and then just opening it up for comments and questions and discussion. So that's the general game plan ahead. So I am in the environmental studies department at Wellesley College. I'm trained as a historian. My first book was actually a book about protecting public lands, about wilderness, about some of those really beautiful places up in the High Sierra. And after I finished that book, I wanted to do something kind of as different as I possibly could. And so I figured, well, what could be more different from wilderness than batteries? And so that was the direction I went. And I was kind of spinning my wheels trying to figure out how to write a book about batteries, actually for quite a few years. And what really kind of, sorry, there we go, kind of turned or flipped the switch, I suppose, for me was the Green New Deal and just how important that was in reshaping discussions, public discussions around climate change in 2019 when Ed Markey, senator from Massachusetts, Alexandria Ocasio-Cortez, representative from New York, introduced this resolution, to provide, a big picture approach to addressing not just, climate change by doing things like, moving towards 100% renewable electricity, but tying that to a much broader social agenda around a fair and just transition. And, for students at Wellesley College, where I teach, I mean, this was electrifying, right? This was just a really exciting, progressive, visionary approach to thinking about climate action. And as a historian, what got me interested too was that it was, clearly playing off of the massive projects and government investment and just social muscle that went into the New Deal in the 1930s. And so this is just a little bit of text from the Green New Deal, where it specifically evokes, that mobilization, national, social, industrial, economic, that was so important during the 1930s and into the Second World War. And, we could spend a lot of time just talking about the history of the New Deal. But one thing that stood out to me is that, the New Deal was about, creating jobs and building, making lots of things, investing in infrastructure, right? Dams and airplanes for the war effort. And, as I started to think about that, what I realized that, for everything that was really exciting about the Green New Deal, kind of one big piece of the puzzle wasn't being talked about very much at all, which was that if we were going to kind of build solar farms and wind farms and deploy electric vehicles kind of on the scale of that New Deal, right? As part of this Green New Deal, we were going to need a lot of stuff, a lot of material, right? We were going to have to make a lot of things to actually do this. Whoops. And so, you know, people started kind of pointing this out, right? That, the expansive scope of the Green New Deal was going to drive up demand for the materials, the metals that are important to these clean energy technologies. And so this is just a chart from a World Bank publication on this topic, which projected that we'd be looking at a, roughly six-fold increase in demand for energy relevant materials by the middle of the 21st century. And so for me, batteries suddenly kind of became important to think about historically because batteries were going to be key to this energy transition, to enacting and kind of making good on the Green New Deal. But they're also the most materially intensive of all of these technologies that were important to the clean energy transition. And as a historian, batteries have a really long history. And so that's kind of how I got into this project, to help think through the material consequences of an energy transition. And batteries go back to the start of the 20th century. I mean, today we still worry about keeping our cell phones charged, but back in the 1910s, 1920s, when wired telephones were first becoming widely available, they ran on batteries back then. You had to put in tri-cell batteries into the telephones on a regular basis. The earliest electric cars were often electrically powered cars up until the middle 1910s. There were as many electric cars on the road as there were gasoline cars on the road. And, popular appliances like the phonograph and the radio ran on batteries initially as well. So batteries have this really long history. And, as someone who is a historian by training, I get excited about kind of geeky intellectual concepts as well. And, for me, it wasn't just the practical matter of, understanding the history of batteries, but also how can batteries help us think more carefully about energy and energy history. And there are just two ideas that are really important to this book. And one is that, a lot of energy history had always treated batteries as a footnote because they actually deliver so little energy, right? Batteries hold very little relative to other major sources of energy, and so they have been treated as a footnote. And so diving into batteries was a chance to really explore kind of the second theme, which is that even if they contain a very small amount of energy, they're key to enabling all sorts of other technologies. They're an enabling technology, right? They make possible the portable electronics. They actually make it possible to start a gasoline-powered car, but they can power an electric car as well. Or they could power a Sony Walkman back in the day or an iPhone today, right? Batteries are this really important enabling technology for all of these other applications. So even if they're really small in terms of the energy they deliver, the quality of that energy, right? Its portability, its instantaneity make it exceptionally valuable to us. And so those are kind of two themes that I play with in this book. The book is organized around three different case studies. It's organized around lead acid batteries, dry cell, AA disposable batteries here in the middle, and then lithium ion batteries on the right side of this slide. So what I thought I'd do is just take another kind of 15 minutes or so and just kind of give you the high points for each one of these case studies. So starting off with the lead acid battery here on the left. So lead acid batteries are probably the oldest kind of commercially sold battery, invented in the late 19th century and really scaled up use with the development of the electric starter for gasoline cars in was it 1916? Right around then. And because of their use in cars, right, all of our cars, even most electric cars, still have a lead acid battery in them for starting and for lighting for the 12 volt electrical systems in that. Because of the ubiquity of cars, lead acid batteries just kind of grew in as an industry over the course of the 20th century. And today we worry a lot about where materials for batteries are going to come from, but that was not a concern with lead because at the time, the world's largest lead mines were located in Oklahoma and Missouri. And we're talking about massive underground lead mining operations. This is a picture from one of the mines in Missouri in 1940, and you can just see how absolutely cavernous it was. This little dot here, actually, there's the person right there. Um, and so most of this lead initially to supply the US lead acid battery industry came from mines in the US, but still mining was hard, mining was expensive. It was a lot of work to process all of that lead. And from an environmental sustainability perspective, what is interesting is that lead, right from the start, became a very valuable commodity to recover and to recycle. And so these are advertisements from the Waste Trades Journal from the mid 1920s, where they're advertising and asking people to return lead back to smelters so they can process it and sell it again for the manufacture of new batteries. And so one of the very earliest forms of what we could describe as urban mining today started with the lead acid battery industry. If you follow this story up to present, which I do in the book, the lead acid battery industry will tell you that they are the environmental kind of success story of the modern era, that they've closed the loop on lead acid batteries as this flyer from Johnson Controls, which was in this business in kind of the 2010s, that they've really closed the loop on this industry and that all lead that kind of gets recycled, gets processed and put into new batteries. And their claims are largely true. The statistics for the United States are that something like 99.5% of all lead acid batteries are getting recycled. Of course, the concern, and for good reason, is that lead is toxic and poses a grave threat to people who are exposed to it. When it's volatilized during the refining and smelting processes, whether that's to make new lead or to recycle existing lead. And so part of the story I tell is all of the health challenges that come for the workers and the communities that are on the front lines of the lead industry. And even if we're recycling 99.5% of the lead acid batteries in the US, when you're dealing with something like lead, even losing, that small fraction that's falling out of this closed loop is really concerning. And so one of the important stories that I tell is how a lot of the lead acid battery industry got pushed out of the United States in the 1990s up until present. And one of the places that's implicated in the global lead trade is Peru. And this smelter in La Arroya was connected with just a really devastating epidemic of childhood lead poisoning. And this issue hasn't gone away. There have been a lot of regulations put in place. The lead industry, operates under very tight scrutiny in the U.S. Still, there are good reasons to continue scrutinizing it. But it's still involved in this international lead trade. So just last week, or I guess the week before Thanksgiving, the New York Times covered this issue in great depth and did a really outstanding job of tracking the connections between the US lead acid battery industry and how some of the batteries are leaving the US and going to countries in Africa where the standards for processing the batteries are just much, much lower than they are in the US. And, this is kind of the most recent example of this, but there is a very long history of pushing lead outside of the US where it has caused harm to communities elsewhere. And so the importance of, following these supply chains, even when it's something that is supposed to be recycled, remains very important. Recycling doesn't necessarily mean that it's sustainable. So that's just a little bit about the lead acid batteries. And, you know, the kind of the cautionary tale of this recycling success story. So let me turn to the second case study, take a drink of my tea, which is focused on the disposable AA, AAA 9-volt batteries that it seems like so many kids' toys still use these days, but not as many other products do. Um, what's really, there are a bunch of things that are really interesting about this, if you're curious about batteries. And one is that the size of a AA battery was actually codified back in 1937. And in part, it was in response to concerns from the military. They were dealing with so many different sized batteries. They wanted it to be standardized to make it easier for managing the supply chains that they depended upon. And so the AA battery, is this very small consumer product. It's not what we usually think of as infrastructure, right? When we usually think of infrastructure, we think of big power plants and, lots of electric wires, connecting those power plants to our homes or dams or highways. But the AA battery, because it was standardized so early, became a form of kind of distributed infrastructure where products were being designed around that standard. And it became interchangeable, right? Anywhere in the world, you can go and pop a AA battery into your camera flash. If it needed one, and it would work. And so just there's a really interesting story of standardization and how that was important to the rise of these disposable batteries, which really kind of enabled kind of electronics consumer culture in the post-war era. The earliest batteries were zinc carbon batteries. Depending on your age, you may remember these batteries leaking all over the place and dying every time they got cold and just really being pretty difficult to work with. The military was concerned about this as well, and the military pushed for better battery chemistries. And out of that research and testing and kind of after World War II emerged the alkaline manganese battery, which Duracell brought to market. And so Duracell with its copper top is still with us, but this is an advertisement from 1970 where Duracell is really drawing a comparison between their newer alkaline manganese batteries and that battery from the zinc carbon batteries, which really were essentially the same technology that had been invented back in the late 19th century. And the Duracell batteries and most of our batteries are now alkaline manganese. The disposable ones hold their charge much longer, much more reliable. They're much less likely to leak. And the leakage, where they would lose their electrolyte, they'd kind of bleed out and lead to corrosion and electronics. I mean, that was a real problem, a real concern for consumers. And so that Duracells were much less prone to that was a real marketing advantage. But to accomplish that, Duracell had to do two things. And one is they had to produce a much more highly refined version of manganese, which I'll let you read about in the book if you want to. But the other thing that they needed to do to stabilize the battery, to keep it from leaking, is they needed to add mercury, which helps stabilize the battery and keep it from swelling. And mercury too, right, is highly toxic. But this was really important to bringing this alkaline manganese battery to market. They started adding mercury to the batteries. About 1% of an alkaline manganese, a Duracell battery in the 1970s would have been mercury. And this is a study from the Environmental Protection Agency from the early 1990s. And it shows US consumption of mercury. And the largest use of mercury in the US was in the chlorine and caustic soda manufacturing industry. But the second largest use was in batteries. And the concern was that of all of these products, the batteries were the ones that were most likely to be thrown in the trash. And some of that trash was being incinerated. And there were concerns about the level of mercury exposure, right? The amount of mercury that was turning up in fish and in lakes, especially in the Northeast and in the Midwest. And it turned out that one of the kind of major sources of this mercury contamination was coming from the batteries. And unlike the lead acid batteries, which are fundamentally lead, the mercury was just an additive in these alkaline manganese batteries. And through a lot of engineering work and a lot of actually cooperation across the big battery companies, they engineered a mercury-free battery, which came onto the market in the 1990s. And so that, so what's interesting here is it's a real environmental success story. Companies cooperated, managed to phase out mercury, and really solved an important environmental problem. The catch, I'm a historian, I always look at the complexities, I always find the catch. It turned out to do this took an absolute, just tremendous amount of energy. So the units aren't so important here. This is from a life cycle analysis that was conducted at MIT on behalf of the battery industry. And what this life cycle analysis shows is that when you add up all of the processing that went into sourcing the ore and processing the ore for the manganese and for the graphite, for the carbon, for the zinc that go into these batteries, it takes about 66 units of energy, megajoules per kilogram that of battery that you have. But here's the real kicker. It takes that amount of energy to make the battery. The amount of energy that you get out of the battery when you put it into your remote control or maybe into your pen flashlight or your children's toy is only a half a megajoule per kilogram. And so to produce this highly refined, very stable, very reliable AA battery takes about 130 times more energy than you actually get out of it. And so when and so that's really a stunning amount of energy, right? You put 130 times more in than you actually get out. If you were using coal-fired power to make these batteries, this would be by far the most polluting source of energy you could find. I mean, it's a really good thing. We don't run the world on AA batteries, but it takes that amount of energy to produce such a stable consumer product. That you can put in a plastic shell for 10 years and pull out, and it's gonna work in your remote control. So those are some high points about the lithium or about the AA batteries. All right, so one more case study I'll tell you a little bit about, and then we can open things up. And that's the now today completely ubiquitous lithium ion batteries, which is probably in all of the devices that we're using to communicate with one another right now. But lithium ion batteries have a pretty recent history. The original research was done kind of starting in the 1970s. They were first commercialized in camcorders and a Sony camcorder in 1991. In 2019, the Nobel Prize in Chemistry was given out to the scientists here on the screen who did the basic research on the anodes and cathodes of lithium ion batteries. And you know, and I guess I put these folks good enough, Whittingham and Yoshino, up just because they were rightfully awarded the Nobel Prize for this work. But the story of commercializing the lithium-ion battery wasn't some big breakthrough in electrochemistry. I mean, it's really a story of small incremental improvements and engineering to kind of make them work in consumer products. And in the book, I describe kind of a ladder of implementation where it started off in small consumer electronics and slowly scaled up, right? So we went from consumer electronics to laptops to electric vehicles and now grid scale lithium ion battery facilities, right, that are storing electricity as part of leveling out supply and demand on the grid. And so there's just been a real kind of ladder of implementation over the last 3 decades. There have been improvements in lithium ion batteries, but not exponential improvements in lithium ion batteries between 2008 and 2020, just to kind of take one time period. The performance of these batteries got better, but by a factor of two. But if you think about your smartphone and kind of how much more you were able to do with it, right, between 2008, which was about the time the iPhone was introduced, and 2020, 20, right? I mean, the capabilities of what we could do with these battery powered devices just improved tremendously. And so back to that theme of enabling technology, kind of thinking about the ecosystem that these batteries live in, the reason that our smartphones became so much more useful, right, is that the performance of the graphics units, the graphical processing per watt, like how much processing could you get out of 1 watt of energy, that improved by a factor of 100 during that same time period. So even if the batteries didn't get all that much better, a lot of the electronics that they were powering became much more efficient than had been the case, which has made our phones and a lot of the portable devices that we rely upon just much, much more useful and capable. And it also led to increasing scales of manufacturing of lithium ion batteries, moving from consumer electronics into these other industries. That pattern also gave, actually, before I'm going to, sorry, I'm going to hold up before I get to that point that I was going to. Part of this is, as you're gathering from this book, I'm really interested in the materials. Like, what's the stuff that goes into these different battery technologies? How does it connect us to different parts of the world? And we think lithium, right? Because lithium is in the name of lithium ion batteries, but it turns out when you look at what actually goes into a lithium ion battery, lithium's super important. It's the in the electrolyte and the anode and the anode and the cathode, and it's kind of the shuttle ion that's moving back and forth to charge and discharge the batteries. But it actually only makes up a very small portion of the mass of the battery. It's, if you're holding a battery, what you're really holding is just a tiny little bit of lithium and a lot of other things like aluminum, graphite, and then some other supporting materials. Lithium ion batteries come in different flavors, kind of like ice cream. Uh, the lithium iron phosphates become more common, especially coming out of China, but now being deployed more in the US in, in a variety of applications. Often higher performance electric vehicles have nickel-based lithium-ion batteries. And again, just to kind of give you a point of comparison, the lithium is a small portion of the mass of the battery, but these batteries also have lots of graphite and lots of aluminum. The nickel-based batteries tend to have cobalt in them as well. And you can see that cobalt is here is a small but important component of these batteries, nickel, and then some other materials as well. So, it's important. And in the book, I explore kind of where the lithium comes from and how it's produced. It's very different whether you're looking at Australia, where it comes from hard rock, or you're looking at the South America, where much of it comes from brines that are pumped and evaporated and processed. But it's also a story of looking at, all the other materials that are important, the cobalt, the nickel, and the aluminum, and understanding kind of how these batteries bring all of these different pieces of the world together to provide the functionality that we expect of them. It also brings up the kind of geopolitics of the clean energy transition, because where those materials come from, where they're getting processed is historically has over the last 25 years has not been the US, right? China, Asia, because of the investment in consumer electronics manufacturing, invested heavily in lithium ion batteries before uh, the US did. And this makes it different from the lead acid and the disposable battery stories. Both of those technologies are manufactured in the United States for a very long time. But China, from the start, and as you can see on this bar chart, which shows kind of the mining industry, the midstream chemical refining, the cathode and anode manufacture, and then the actual battery assembly. And this is a chart from 2020. You can see that China has the lion's share of the market in these key kind of manufacturing stages. China doesn't have a lot of mining, but China, through its Road and Belt Initiative, kind of 2010 to present, has built very strong connections to all the different parts of the world where the nickel, the cobalt, the aluminum, and the lithium is being sourced from, so that they are actually, bringing in most of those raw materials for processing in China. And so, this is part of that story of how China has become a dominant player in most of these clean energy technologies, certainly the lithium ion batteries. So so that kind of wraps up the kind of big points that I wanted to share about lithium ion batteries, just kind of ending with that point about the geopolitics. Um, and you know, just kind of stepping back out to the overall frame of the book, as I mentioned, a big piece of this is just understanding how these technologies that we rely upon, how it connects us to the periodic table, but also all the places that we source all of these materials from, whether it's the lithium or the cobalt or the lead or the graphite. I mean, each one of these elements is sourced commercially from different parts of the world in very different ways, and poses different kinds of sustainability challenges. So understanding the implications for the communities and the workers that are involved in this work is important, both to understanding the history of and the challenges we face going ahead as we rely more on these materially intensive clean energy technologies. So just to move towards wrapping up here, three lessons that kind of come out of this project, out of this book. And one, I think, I've already been emphasizing, but it's that, moving to a clean energy future is going to require a lot of increase in material use. The lithium, the cobalt, these clean energy relevant materials we've been talking about. I don't have it on the screen, but there's no question that that is better than the status quo, right? Where we're burning fossil fuels, which we use once and are gone, right? It's much better to be using these renewable energy technologies, but we're going to need a lot of material to manufacture them. And it's not something we can recycle our way kind of out of. We have to source those materials first before we can start to recycle them. And so kind of owning up to that challenge that this is not something we can recycle our way out of. I think that's one lesson that I drew from this work. The second one is the environmental justice dimension of this, right? I mean, these will move us towards a more sustainable fossil-free future. But historically, extractive industry, fossil fuel or otherwise, has disproportionately impacted communities of color and the poor in the United States and elsewhere in the world. And we're shifting, and have been shifting, although this has changed somewhat, but shifting this extraction abroad. And so keeping concerns and kind of auditing and spotlighting supply chains to ensure that these materials for sustainable technologies are sourced in ways that are more just than has been the case in the past. I mean, that's essential work. And so that's the second lesson. The third one is that we need government policy to support these technologies, this energy transition, a domestic battery industry, and it's not just about the manufacturing, but where we source the materials from. And for anybody who's been paying attention to these issues, we've seen an enormous policy roller coaster over the last 4 years. When I published this book in August of 2022, I kind of ended with a kind of rallying cry for good policy to help do this kind of work. The same month, no connection obviously to my book coming out, but the Inflation Reduction Act was signed into law by President Biden. And in many ways, it did a lot of the work that I was calling for in this book. I as this was happening, I was just excited to see, as an observer, just how much activity there was suddenly, with good policy and good support that we were seeing in 2021, 2022. And, as someone who'd been watching this industry pretty closely, I suddenly just started to become overwhelmed with like how many announcements there were of big new projects meant to scale up a clean energy battery supply chain. And so I kind of, when I finished this book, I pivoted to actually just taking all of this information and just trying to track it, trying to track what was happening in real time with the battery industry. And so this is just a snapshot of a spreadsheet of the work I was doing with students, trying to itemize all of these battery projects and how many jobs they were promising and what they were going to be manufacturing. And using that database, my students and I, we started putting out updates on kind of what's happened, right? We've had this big law that was passed in August of 2022 to support clean energy transition and scaling up electric vehicles and batteries. Well, was it working? And so this is an update from June 2024 showing a map of all the new projects across the United States that were moving into the battery supply chain. 107 projects at that time, $90 billion in investment, and 57,000 jobs had been announced, right? And so, this is, for people who are focused on this, is super exciting. We have since pivoted since the policy environment has changed dramatically, and we're now tracking the slowdown in projects now that we've seen such an abrupt shift in federal policy. And so here, all of the red circles are projects that in the last 10 months have slowed down. Many have advanced, but we have seen a substantial slowdown on account of the changed policy environment. Oh gosh, so I hate to end on the kind of policy politics note there, but I think these are all the points that I thought I'd share just to open things up. I guess I have one last slide. Just if you want to explore any of the tracking that we're doing, it's at this website, which is called The Big Green Machine. That's the name of the website. If you Google it, it brings up an interactive dashboard where you can explore both what's advanced and what's slowed down and what the clean energy supply chain looks like in the United States. And I guess just before I wrap up, I'll give a shout out to my Wellesley College research students who've helped me with all of this tracking work that we've been doing over the last 3 years. Um, and so with that, I'll say thank you and I'll stop. And Jack, yeah, I'm ready to hand it back off to you.
Thank you so much, Dr. Turner, for that thought-provoking and illuminating presentation. Really appreciate your time and you lending your expertise to this program. We will open it up for questions. So I already have one in the chat. We'll start with that one. And then I know I have a couple written down as well. And then afterwards, if you feel like you want to unmute yourselves or raise your hand via Zoom, please feel free to do so as well. So the one in the chat that we have can you please comment on the current status of solid-state lithium batteries?
That's a great question, right? I mean, solid state lithium ion battery would bring significant improvements if it could be done, kind of at a cost comparable to existing battery technologies. And so I think a lot of people are eager, is there going to be a breakthrough that's going to bring that technology to market? I am a historian. I am, so I get to make the excuse that I'm really bad at predicting the future. I'm also not an electrochemist, and I don't have a deep knowledge of kind of the chemistry of or kind of the near-term prospects for the solid state batteries. What I will say though, just based on kind of what I've learned exploring and kind of putting this book together, is just how much work goes into um, verifying, to securing, to kind of vetting these technologies right before they're brought to market, right? So I talked about a ladder of implementation where the lithium ion batteries started with small applications and then have been scaled up, and kind of moving a new technology like the solid state batteries to market at scale where automobile manufacturers are going to be willing to put an 8-year warranty behind them. That takes a lot of time, and given kind of how entrenched the lithium ion batteries that we have now, which are not solid state, right? They're based on organic electrolytes. But because they have so much momentum, right? My guess is that we will see that momentum carry forward, even if solid state batteries offer a significant improvement. But I don't consider myself an expert on that. And yeah, but that's my quick take.
Thank you, Jay. Another question in the chat, which is kind of similar to another one I had. Kathy asks, you mentioned the recycling rate of alkaline batteries and I believe lead acid batteries as well. What is the recycling rate of lithium batteries? And I might add, kind of what are the critical lessons that maybe we can draw from the history of, recycling lead batteries that could be uh, applied to create a more circular economy for
Yeah.
those lithium batteries?
Yeah, that's a great, good questions all the way around. So I don't have a number that I can kind of quote for you on recycling rates for lithium ion batteries, in part because it's, I mean, it's complicated, and that so many lithium ion batteries, I guess most of the lithium ion batteries that have been manufactured have gone into cars. Most of the batteries that are in cars are still in service, right? So they haven't been recycled yet. So we don't actually know. Clearly they've been used in consumer electronics for a long time, 3 decades at this point. There are varying estimates of what the recovery rate for lithium ion batteries has been. And I'm blanking on his name, but there is a scholar, Hans, somebody in Europe who's done really outstanding work researching the different recycling rates for lithium ion batteries. And his analysis indicates that it's much higher than kind of early estimates, which put it at a relatively low figure. Um, so I apologize. That all seems a bit ambiguous. But I think maybe to come back to that question you were asking, Jack, when we look forward, kind of taking what we can learn from the history, my guess is that we're going to see recycling rates for lithium ion batteries that are much more comparable to the lead acid batteries as opposed to the consumer products, to the, recycling rates for AA batteries. Because these, large format lithium ion batteries, similar to the lead acid batteries, are going to be handled at service centers, at automobile, repair centers, and places where it's easy to consolidate and move the batteries back into the recycling chain. And so I think that's one reason, right? They're gonna, it's not going to depend on a lot of consumers deciding to put them in a yogurt tub in their closet and then bring them to the recycling center, right? They're going to be at a, already kind of part of the recycling supply chain, since they'll be at a at a commercial facility. So I think that's one piece. The other piece is that the materials in the lithium ion batteries are valuable. And that was always the problem for recycling alkaline batteries, is that they weren't particularly valuable. There wasn't much in there that was kind of worth recovering. Whereas with lead acid batteries, it's actually cheaper to recycle and get the lead from recycling than it is to source the lead from the mine. And so I think, the economics, and the infrastructure work in favor of a very high recycling rate for lithium ion batteries. Um, yeah. So, and we're seeing a lot of this, right? I mean, there have been big investments in companies that are working to recover lithium ion batteries. Part of that's, they're anticipating the future supply of spent batteries, right? When the batteries in EVs die. But there's also been a very high, kind of failure rate in the manufacturing of batteries. And so they recycle the batteries that don't make it all the way through the manufacturing process as well.
Lovely. Thank you again. Another question asking what kind of batteries can be used in the storage of electricity from solar panels so that the electricity is available when the sun is not at its peak? I might kind of broaden that question again, Jay. For the average citizen or for the people on the call who want to maybe adopt more renewable energy kind of avenues, such as installing solar panels, how can they practically and even ethically take advantage of those technologies? I'm not sure if that's within the purview of your work, but I'm curious if you're able to answer that bit.
Yeah, well, so the batteries that are being used now in most kind of household scale, storage products. So this would be the Tesla Powerwall, or a company like SolarEdge, which manufactures its own, household scale battery storage, or Generac, right? The company that does backup generators. They also have storage batteries. All of those are lithium ion batteries, likely a lithium iron phosphate battery, which is a little bit less expensive, a little bit heavier, but also more stable, right? Because fire is, one of the key things. Any fire risk has to be engineered for and minimized. And so, if that's what you're, if, if somebody purchases one of those products to help provide for energy management, that's the technology they're relying on. That is something that personally I would do, despite all the kind of questions and concerns I'm raising about the supply chain. I think, adopting these technologies and facilitating a transition to a cleaner electricity grid, that's all important work to do. But I think at the same time, right, asking companies, where are you getting your materials from? Is there cobalt, right, which is, could be sourced from the Democratic Republic of the Congo? Does this battery technology contain cobalt? Encouraging legislators to adopt laws and policies that require transparency in supply chains, that's the other important part, right? For people who care about sustainability and social justice, right? We need to use these technologies to advance the clean energy transition, but we also need to make clear that there's a strong demand for doing this in a way that's more just and more sustainable. And so I think, they're two different actions, but they're both essential for people who want to do this and make a difference at the individual level.
Awesome. I think we have time for, I just want to ask one more question about this idea of a just transition before I let you go. I know you're on a hard cap, Jay. So I know the work that you're doing emphasizes this idea of a just transition, and I think if people on the call tonight have been to some of our previous sessions, we've talked about that idea a lot. But based on the history of batteries, I'm curious what specific actionable policies can be implemented to ensure that these frontline workers and communities that are not bearing the brunt of this new environmental and or social risks in the supply chain, if that makes sense.
Yeah, I mean, a lot can be done. And I think, one big piece of it, I think just often when people, think about being responsible consumers, kind of what folks tend to think about, I think I often think about is like, how do I recycle this thing that I already have? But, one of the big points here is that it's not just about the recycling. We need to think about where the materials are coming from in the first place. And there's been a lot of work to kind of daylight the issues of social justice that are entangled in these different supply chains, whether it's lithium or cobalt or graphite. And so, what policies can be supported? I mean, some of it's not about policy. It's about, pushing companies to, well, I guess not governmental policy, but, pushing companies to take responsibility to participate in third-party certification systems that, help validate that the products they're bringing to market, have been sourced in ways that are more responsible. There's a group called the um, IRMA, which is the Responsible Mining International. I'm forgetting the details of the acronym all of a sudden, but Responsible Mining Assurance. They have done a lot of work to provide certification schemes and audit strategies to allow companies to certify that their supply chains are, going to reflect best practices. So that's one strategy. Another is to, there will be change in Washington, D.C., and there will be more opportunity to push for good governmental policy. And I think there were elements of the Inflation Reduction Act that focused on bringing these industries back to the United States, bringing kind of rewarding companies that worked with countries that were free trade partners to the US that tend to have higher standards for occupational health and safety, and continuing to support and push for clean energy policy that does include those kinds of provisions in around supply chains and issues of worker safety and health. That's important as well. So I think, there are a bunch of different tools that are available, but I think, it's also important just to keep raising the question and, pushing companies on this and making clear that, it's not enough to be sustainable, but we need to be thinking about the social justice. I mean, that's intrinsic to what, what is truly sustainable.
Absolutely. Well, Dr. Turner, I will get you out of here. But I want to thank you again for your presentation and your time and sharing your expertise. It was really a treat to have you with us tonight. A reminder, the book is Charged, A History of Batteries and Lessons for a Clean Future. It is currently at the library. We just got it in, so please check it out. It's a great read. Um, Jay, thank you again. Can't thank you enough. Really was a pleasure to have you tonight. And for those in attendance, really appreciate you coming out and spending your evening with us.